We're going to start with another former JGR editor, George Reid, and Bob McPherron is going to talk about George after this clip.
Magnetospheric-Ionospheric coupling is an enormous subject. We've heard just one or two aspects of it discussed today, and I'm going to discuss just really one or two other aspects, which leaves several hundred aspects completely untouched, and I hope some of these can come out in the later discussion. My talk is really confined to the situation taking place in the polar caps, in the vicinity of the polar caps. And it must therefore include solar wind coupling as well as simply magnetospheric-ionospheric coupling. And I'm sure I don't have to apologize for including the solar wind in this session. Disturbed conditions, which is the title of the session, implies a time-varying situation, and that the time-varying situation is an essential element of the whole process and will be our chief concern here. As I understand it, the role of one of the lecturers at this conference is to act part as a tutorial lecturer and partly as an agitator. And I'll try to do a little bit of both. I'll try to throw in some outrageous, controversial stuff, which I'm sure will bring Vitainus leaping to his feet, if no one else. And the ultimate driving force I'm talking about, of course, is the momentum of the solar wind. I don't think anyone would argue with that. There is now accumulating evidence that the momentum of the solar wind, in order to be efficiently applied to the magnetosphere-ionosphere system, requires that field line reconnection take place. That is, you can have all the solar wind momentum you want in the absence of field line reconnection. Nothing much is going to happen. But once the field lines are reconnected so that we have a direct connection between the interplanetary field and the geomagnetic field, then effectively there's a path available for the momentum to enter the magnetosphere and drive the system. And the third little piece of evidence which helps in a way is in a recent study of polar cap magnetic records, Maezawa, I think this work's still unpublished, but it's on the verge of publication. Maezawa has, I think it is. I don't think Maezawa is here. People are beginning to find that reconnection is a very patchy process, that it's not something that takes place over a well-defined reconnection line on the day side of the magnetopause. And I think, again, intuitively, this is a reasonable sort of thing to expect. Reconnection is a thing that I feel the magnetosheath plasma would rather not do if it can possibly avoid it. It's much easier for the plasma to simply slip around the flanks of the magnetosphere. This isn't nearly as elaborate as Walter Heikkela's diagrams, but it's it's enough to show the purpose, and I'll be showing it once or twice. The classical Axford-Hines type theory of convection with reconnection added to the picture, of course, involves a southward magnetic field in the usual picture, but of course it works with any orientation. With solar wind plasma being convected in here towards a stagnation point at which field line reconnection takes place, forming an instantaneous field topology like this. And these field lines then are carried by the solar wind back across the polar cap and downwards into the tail lobe region where they reconnect at a reconnection line here. And then the convection proceeds back in towards the Earth around the flanks of the magnetosphere and back out to the reconnection point on the day side. Now that's the simple picture, which I don't think people have too many objections to these days. It's something that probably goes on all the time and is part of the lore of the field, in a steady state at least. Well, now what happens when the field line reconnection rate changes in the vicinity of the dawn polar cusp region here. What happens, first of all, of course, is that an Alfvén wave, or something like an Alfvén wave, is launched down the reconnected field lines, informing the plasma as it goes that there's a dE by dt accompanied with it, that the field is changing. And that excites a polarization current, J, which is proportional to dE by dt. And the Lorentz force, J cross B, associated with that current, then starts to accelerate the plasma in the anti-solar direction to try to get it up to the new speed that the reconnection rate is demanding. Flux must be pulled out of the reconnection region at the same rate as it's being pushed in. Well, when this wave reaches the current, the dynamo region of the ionosphere, the Pedersen currents start to interfere with it, of course. And there's, well, in radio wave terminology, a mismatch occurs, and a reflected wave travels back up, telling the solar wind that it can't get going, and the solar wind should slow down. Well, the solar wind doesn't want to do that, of course. It's much more powerful, so it launches another wave back down, and there's a successive series of reflections of these waves until the whole thing reaches a steady state. And this whole picture was first analyzed by Hines and Story many years ago, back about 1958, in the course of a lengthy argument with Gene Parker in the pages of JGR.
I didn't know George very well, but it was certainly interesting to start with this video as I'd been asked to talk about him. And he said, well, here in this session where we're going to talk about ions and what they do in the world, he says, we should first start with talking about magnetosphere solar wind connection. And of course, that gave me inspiration yesterday and an explanation of what I was going to do. The first actual encounter with George, as you noticed, George is no longer with us. Had he had the opportunity to come, I'm sure he would have enjoyed being here. He loved the outdoors. He was well known for his cross-country skiing and downhill skiing. And that's my first remembrance, actually, of George Reid, was on a trail out behind Boulder, climbing up to Mount Toll. And I remember meeting him coming up as we were coming back down. We exchanged a few words. I knew him only as much as you see here by listening to his talks at meetings and so on. I think, well, let's look at a few of the things that we know about him. He had a very broad interest in the atmosphere and the ionosphere, its dynamics and its chemistry. He's best known, according to the literature, on the invention of the term polar cap absorption. And that's what happens, you know, that's why they divert planes from going over the polar cap when we have a solar proton event, because the bombardment just completely wipes out the ionosphere as far as radio communications are concerned. So polar cap absorption, or PCA. He had many, many interests: solar energetic particles, solar influences on the upper atmosphere, ion chemistry, noctilucent clouds, the dynamic and chemistry of the middle atmosphere, the mechanisms of global climate change with emphasis on the tropics, and the influence of solar variability on the lower atmosphere and ocean temperatures. And it's actually, that is the second memory I have of George. I remember at one talk or something, I walked up to him. This was at the beginning of the whole business with global climate change and things, and I talked to him about, man, what are we doing to the world? And he looked at me with a little bit of, he said, well, perhaps we should consider this in a little bit more detail. And I got the impression that he was not a proponent of man as the influence that was changing climate and so on. And if you look back, there's a series of about 5 papers that he wrote in between 80 and 2000 on the topic of solar variability and climate change. And it's interesting to see the progression, because as we gathered more and more data about the sun, and his last paper, of course, we already had almost couple solar cycles of observations in the outside the Earth's atmosphere of the radiation from the sun, and it was becoming clear even at that time that there wasn't a very large variation during a solar cycle, about a watt or something out of 3,000, that it wasn't a big change. And now the question is, how much was the baseline changing? And that's the argument even today now with 3 cycles of data that I've seen the people trying to displace the total irradiance of the sun's measurements up and down because the 2 satellites don't always overlap and whatnot. So it's a big problem of trying to get the baseline. But I've seen extrapolations that there's a slight increase, there's a slight decrease, and it's probably just as good to say it's been constant. So what we have for the time that a lot of temperature change has been occurring is the solar cycle variation. And in these papers, George made a big point about the complexity of trying to untangle all of the different processes that might lead to the sun if it didn't have a lot of variability in actually influencing climate. And he particularly was interested in the sea surface temperature and whether it exhibited in the influence of the solar cycle. And there was some evidence that that was the case. The ocean, of course, is 70% of the Earth. You've got to take into account what it does as far as absorbing heat and so on, and then transporting heat around. And that was the main point of a lot of this work down here that he was involved in. The 2 focuses that I've just been talking about were ozone depletion and climate change. And here's the statements that I just made. I think that towards the end, he began to realize that we weren't going to solve the problem. As far as solar activity and how it influences the Earth through geomagnetic activity, if you've looked at the complex models that we have of how, oh, well, solar protons create NOx, the NOx gets caught in the polar vortex and it comes down and a gravity wave interacts. And you begin to look at these 8 or 10 step processes and you ask, how can you convince anybody that you got to change your behavior when it is so difficult to work out mechanisms that might be the cause? I don't think that, certainly I never knew whether he came to any conclusions about that. It was interesting that he started his lecture with an apology that at that time, in 40 years ago, that there were about 200 topics that he couldn't get into. We've got 40 years more of data. And I kind of wonder what young people do today in order to get through that literature, because, as I said, with substorms in that same length of time, we've had 4,000 papers. I don't think this topic has got quite that many, but it's getting out of control in the sense. I think we're all going to forget how to do square roots, and we'll probably all forget a lot of this original work. That's the only way that I can see. As you heard in this lecture, he emphasized the patching nature of reconnection, and we're seeing it over and over, both on the day side with these auroral channels going poleward. We see it now on the night side with the patching nature of reconnection. And when you do the high-resolution simulations, the tail's just filled with things going off and channels flowing in. So he talked quite a bit about that. He also talked about something that was important to me. In fact, it was the second paper in my list of possible ways the ionosphere might affect the magnetosphere, and that was through impedance mismatch. And of course, impedance mismatch is the difference between the alphane resistant or conductance and the ionospheric conductance. And if it isn't matched, then you get these reflected waves. And I heard somebody ask the question, where does the 20-minute time constant come from? Well, it's L over R, and it's this bouncing back and forth of the waves to bring equilibrium about. And that's where the 20 minutes comes from. We have the same 20-minute sort of time constant on the night side as much as the day side. Well, do we understand the effects of the ionosphere on the magnetosphere? Well, as Rick pointed out, uh, could the ionosphere provide all the plasma out there? The answer is yes. I don't think it does, but I don't know how much it does, and I don't think the magnetosphere cares a lot where it comes from. The problem, though, that George discovered here in climate change is the same problem we have in using our crude measures like the indices and so on, which is the only statistical data we have to actually come up with an answer to, is it affecting it in a very obvious way? Well, as he said, there's still much work to be done, and 40 years from now, I'm not sure 40 years from now this meeting will be meeting, but hopefully it will, and I hope by that time we'll better understand how the ionosphere is affecting the magnetosphere. Thank you.